So today I'm going to share some of my recent works on knowledge graph reasoning with neural networks. So yeah, so let's start. So first, let's talk about what are knowledge graphs. Knowledge graphs are connections of facts between entities. For example, usually you can represent facts in triplets, which you have a head entity, a relation, and a tail entity. For example, like Zhaocheng Zhu is a professor at the University of Montreal, so you have head entity to be Zhaocheng Zhu, and relation to be, for example, professor at, and tail entity to be the University of Montreal. And this kind of structured knowledge graphs has a lot of applications in real world, like ranging from question answering in natural language processing, recommender system, and also very recently, it's also very popular to apply knowledge graphs to drug reproposing, simply because drug reproposing considers a knowledge graph that consists of like proteins in human body, disease, and maybe drugs, so that you can infer new relationship between drugs and disease, and you can repropose existing drugs for new disease. So what I'm doing is knowledge graph reasoning, which is a very fundamental task on knowledge graphs. For example, a simple case of knowledge graph reasoning is trying to ask who is the son of the Queen Elizabeth II, and we look at the family tree of the British royal family, and we find the answer like Prince Edward, Prince Andrew, Prince William, and not Prince William, Prince Charles. And this kind of reasoning task is really challenging, mainly because three aspects. The first thing is that the knowledge graph is typically incomplete. Like here in this case, where we miss the age between like the Queen and Prince Andrew. Although we know that in real world, Prince Andrew is her son, but in some knowledge graphs, this kind of stuff could be missing. So you cannot simply just retrieve the answer on the knowledge graph. And the second thing is that about scalability. If we want to deploy knowledge graph reasoning in real world scenarios, so we need to deal with like knowledge graph of million scales, millions of nodes, or maybe even larger than that. And the last thing is about the inductive setting, which we will want to learn something from an existing knowledge graph and try to generalize to new knowledge graphs. So here I can give you an example of what is inductive setting. So if we want to deal with something like with a family tree, and we train our model on a family tree of the British royal family, and we want to generalize it to Canadian politicians, because obviously both of them are family trees, and we want to figure out some rules or some hidden structures from one family tree to another family tree. So in this talk, I will talk about my recent two works. One is the NBFNet and one is GNQE. So NBFNet is mainly focused on single hop reasoning on knowledge graphs, while GNQE is focused on multi-hop reasoning on knowledge graphs. So let's start from NBFNet, neural Bellman-Ford networks. So there are three ingredients in NBFNet. The first thing is try to formulate the reasoning process as a path representation learning program. And the second thing is try to compute the path representation efficiently with dynamic programming. And the last step is to parameterize all the algorithms with neural networks, so that when we combine neural networks and the Bellman-Ford algorithm, and we reach NBFNet. So let's first motivate the usage of path representations. So let's think of a philosophical question. How do humans reason about new facts? And we just give a very simple example here. If you try to predict if there is some relation between this red entity, the blue entity, to the orange entity here, so what humans do is that you try to take a look at the structure between them. So, for example, just this very small subgraph here, and in order to express this structure into more simple stuff, so you somehow can express it by the set of passes between them. For example, if you can take a look at this path, you see that this is his wife and her daughter and her daughter. So you can possibly infer that the relationship between the head entity and the tail entity is granddaughter. So if we apply this kind of idea, then what we can induce is that in order to infer the relationship between two entities, what we want to do is to take a look at all the passes between these two entities. And that's our motivation of path representations. And there are many existing examples that we can classify into our path representations. The first very famous one is the personalized PageRank, proposed like 20 or 30 years ago. And this one tried to measure the proximity between two entities in a homogeneous graph. And in personalized PageRank, it measures the random probability from this entity to reach this entity. And you have every edge representing the transition probability from one node to another. So personalized PageRank can be expressed as a path representation, where each path, the value of each path is the product of all the probabilities on that path. So that you get the probability for this path. And then you take the summation of all the passes so that you get the random probability from head to the tail. And another case of path representation is the graph distance, which I guess maybe all of us have already learned in basic computer science course. So in the shortest path distance case, so you try to enumerate all the possible paths between the head entity and the tail entity. And for each path, you take the summation of the length in that path. And for all the paths, you take the minimum of all the paths so that you can finally reach the shortest path between the blue and the orange entity. So more generally, we define the path representations as computing something between two entities by using all the passes between them. Well, we use some generalized operations to do so. So for the aggregation of all passes, we use the generalized summation. And for the evaluation of computation of a single path, we use the generalized product operation. However, although this kind of path representations look really elegant, but the problem is that in general, we cannot compute like that. Because if you consider a non-trivial graph, typically the number of paths grow exponentially with the length of path, so that we have exponential number of paths and you cannot enumerate that. But recall the examples we talked before, like personalized PageRank and graph distance, they can actually be solved in polynomial time. Like for personalized PageRank, there's an algorithm called power iteration. And for the graph distance, I guess maybe you are more familiar, and we have the so-called Bellman-Ford algorithm. So the idea behind these two algorithms is that dynamic programming, so we will introduce that later. So we use the same idea of dynamic programming, but just apply it to a more generalized path representation idea. So recall the idea of what is dynamic programming is try to leverage the distributive property of summation over multiplication. So when you compute something like AB plus AC, so you can take a common factor A out, and then you get A times B plus C. And you can do the same thing for the generalized operations if they are assumed to satisfy this kind of distributive law. And if we project this kind of operation onto the computation of path representations, what we have is like, if we have two passes, and if they share some certain prefix, we can take the prefix out, and we compute the representation of the prefix, and then times by the summation of the suffix. So if we apply the idea of this kind of distributive property iteratively for every step computation of the path, then what we arrive is the generalized Bellman-Ford algorithm. At the first step of the algorithm, we initialize the boundary condition, just something at the source node to compute this kind of path. You can just think of this is very similar to the Bellman-Ford algorithm. You initialize the source entity with 0 and every other entity with positive infinite. And what we do is that we perform a message passage step to reach this one-hop neighborhood, which covers all the prefix of one-hop length. And we can do it for the second hop, for the third hop, for the fourth hop. And here in this example, we only have passes with a maximum length of 4, so we only need to do fourth hop. In practice, in real world logic graphs, typically you just take 6 or 8 hops and you can reach a convergence for the algorithm. So in a nutshell, this can be somehow viewed as graph neural networks, but a little bit different from the standard graph neural networks we use. In standard graph neural networks, we have just some external input, but here, when we want to try to compute some path representations with respect to some head entity, what we do is that we create initial boundary condition looks like this, and we then apply some basic function and get the output. So there are many examples that we prove in our paper that falls into the paradigm of path representations, like from count index, personalized page graph distance, widest path, and also most reliable path. The last two path programs are very famous programs in network routing. And they have also their corresponding formulation with the generalized product and generalized summation operations. And the corresponding generalized Bellman-Ford algorithm sometimes has their name in the literature, and some are just unnamed, but actually all of them can be computed by the generalized Bellman-Ford algorithm. But back to our question of knowledge graph reasoning, we can somehow use this kind of stuff for knowledge graph reasoning, but the problem is that this kind of like the definition of A's and the operations, like the product operation, the summation operations, they are handcrafted. So they might not be optimal for knowledge graph reasoning, especially consider that when a knowledge graph arrives, different knowledge graph may have different semantics. And for a human, you cannot handcraft something easily based on a knowledge graph of a very complicated semantics. So the answer to this question is that we use machine learning, use neural networks to learn this kind of operations so that we can get a better result for the operations. So here is our neural parameterization. We mainly parameterize three components in the generalized Bellman-Ford algorithm to model a given query in a single source fashion, like the single source shortest path. So we assume that the query is given in the form that's given U and Q, and we want to predict all the entity for this UQ. And what we learn is the first component is we learn indicator. That's learn the boundary condition, the initialization condition for the Bellman-Ford algorithm. And the second thing we learn is the message, which is how we define the something transit from one node to another node. And the third thing we learn is about the aggregation function, which is how we combine the messages from one node's neighborhood. And for simplicity, we just use some existing design from existing graph neural networks. Like for the messaging functions, we borrow from existing knowledge graph embedding literature using like trans-E, which is actually a element-wise summation in high-dimensional space. And this mode is element-wise multiplication in high-dimensional space. And the rotate E is just a rotation in complex number space. And for the aggregation function, we simply follow standard JS using something like summation, mean aggregation, or max aggregation, this kind of stuff. And all the components can be just learned jointly end-to-end by the supervision of knowledge graph reasoning. So one good thing about MBXNet is that because we are based on path representation, so we can provide interpretation to our predictions. What we can do is that once we get a prediction, we can ground our prediction to every path. We compute the contribution of every path in the prediction, and we get some like contribution score. And we can take passes with top scores to be the important path for the prediction. So here are the results of MBXNet on standard benchmarks. And this is just a standard knowledge graph completion benchmark. And for the metric like MI, it's for the smaller is better, and for the rest metrics, the larger the better. And we also tested on somehow degenerated case of knowledge graph reasoning, which is the homogeneous graph link prediction. So homogeneous graphs means that there's only one relation across the whole graph. Everything has the same relation. So that can be viewed as knowledge graph, a very easy case of knowledge graph. And we also achieve very decent results on this kind of benchmark. And the last case is for the inductive related prediction. It's the inductive version of knowledge graph reasoning. So it's more like train on one graph and generalize to another graph with unseen entities, but the same semantics. And in that case, we also achieved certain results on that benchmark. And the last thing is very interesting is about the interpretation of MBXNet. For example, if we predict something like a query, Florence has the vacation and discipline, And what we found as interpretation in MBFnet is we found a path like Florence is contained by Italy, and Italy has the capital Rome, and Rome has application of this Italy. So we can probably infer that this Italy has been to Florence. And the second part is very similar, like Florence is the place that Zhaocheng Zhu lived, and Zhaocheng Zhu also lived in Rome. So probably Florence and Rome is somehow connected, and then because this Italy has been to Rome, so this Italy has probably been to Florence. And about the second paper, Jian query executor. So this paper extends the idea of MBFnet to multi-hop reasoning. And the ingredients is try to decompose the problem of multi-hop reasoning into some simple, easy operations. And what we invent here is that we try to borrow the idea of fuzzy sets and try to use it to solve the reasoning problem. I will introduce the idea of fuzzy sets later. And we parameterize the operations with JS, which is actually inspired by MBFnet. And we also parameterize some logic operations with fuzzy logic. So the idea is to combine GN and fuzzy logic to reach GNQE. So let's take a look at the problem of multi-hop reasoning on knowledge graphs. It's formally known as the first-order logic queries. A typical first-order logic query could be which universities do Turing Award winners of deep learning work in? So this kind of question can be actually rewrite as this kind of query patterns, where you try to search these query patterns in your knowledge graph. But you cannot directly search a pattern in the knowledge graph because the knowledge graph is incomplete and some edge is missing. For example, like if you consider a symbolic algorithm from the graph database community, you just search this subgraph in the large graph. You can say start from the Turing Award, start from deep learning, and then we try to search this subgraph. But we cannot reach the answer because some link is missing. Like we found that in the large graph, the link between Jeffrey Hinton and the University of Toronto is missing. So we cannot search this pattern directly on the large graph. And recently, there's a surge of using neural embedding methods for answering multi-hop questions on knowledge graphs. And the idea is to first embed all the entities of the knowledge graph into some low-dimensional embedding space. And in embedding methods, what they do to solve the query structure is that they first find okay, the node for, say, for deep learning is here, the node for Turing Award is here. Then we do something in the embedding space. For example, like the BLE inverse, then we convert to this node. And for the wing inverse, we get this node, and we do something like this is an intersection, just to take the average of them or some weighted average of that. And then we apply the operation of university, and we get the result. And in order to finally decode the result into concrete entities, so we need to do something like a k-nearest neighbor search to say these three are the potential results for that. But the problem of neural embedding methods is like, you can start from some entity, that's okay, but when you compute to some intermediate result, you cannot interpret what it is. And you can also not change the variable if it's not correct, because it's just something in the embedding space. And you know that, say, this node in the embedding space may correspond to some entity in the knowledge graph, but you don't know what the embedding you computed here, like the red one, the yellow one, you computed corresponds to what entities in the knowledge graph. So here we try to solve the problem about embedding methods by using fuzzy sets. So fuzzy set is very simple. It's just a generalization of the conventional set in mathematics. But we have a probability for each element being in the set. For example, a fuzzy set of entities would look like this. So these entities are just excluded from the set, but these entities are in the set, and the different entities have different probabilities being in the set. And when we do some operation like y equals to the university of x, so we take a fuzzy set as input, and we do some operations, and then we get another fuzzy set as the output. So based on the fuzzy set, we define 4 operations. The first operation is the relation projector, which we has already seen in the previous slide. And the other 3 operations are conjunction, disjunction, and negation. So the conjunction is just the logical AND. take the logical AND of X and Y, and disjunction is the logical OR operation, and negation is just take the inverse. And in order to parameterize it with neural networks and can learn it end to end, so we try to parameterize the relation projection with spontaneous networks, and for the rest of the three logic operations, we use for the logic. So for the relation projection operation, we propagated with GN. So this idea is quite close to the idea of NBFNet, because in NBFNet, we have something like a single source initialize the boundary condition, and then we propagate it, and then we get the answer to that relation. And what we do here in GNQ is that we initialize the boundary condition with a multi-source stuff. Like this is multi-source. This is not a single source, and we compute something like a multi-source short distance or something similar to that, and then we reach the answer of this multi-source projected by the relation university. And because we are using a GN to do that, so it's different from a simple symbolic retrieval algorithm that we can deal with missing links in the knowledge graphs. For example, like here, the link of university between Hinton and the University of Toronto is missing. But what we can do is that when our GN propagates from like the age postdoc and the age study at, then we know that, okay, this postdoc studied at the University of Toronto, then he is probably at the University of Toronto. And here are the illustration of physiologic operations. So the physiologic operations are just the non-parametric operations that defined on continuous fuzzy sets. For example, here is the illustration of the logic M, the conjunction operation between two fuzzy sets. Then you take the two fuzzy sets as input, and then you compute the element-wise multiplication of different entity, and then you reach the output. So what we use here is called product fuzzy logic, while you may also try other fuzzy logic systems like Min-Max fuzzy logic, or maybe Lucas Schwader fuzzy logic, if I remember correctly. And in the product fuzzy logic system we used here, the conjunction is defined as the product. And disjunction is defined as x plus y minus xy, and negation is defined as 1 minus x. So every operation just gives output in the range of 0 and 1. And it looks a little bit weird why disjunction looks like this, because in all fuzzy logic systems, they want to satisfy some common logic laws. For example, like with this kind of operations, they can recover the Morgan's law that when you change the order of conjunction and the negation, then you get something like the disjunction and negation. So combining this together, and then we reach the model of GNQE, and we benchmark it on the standard data sets. And like this kind of benchmark is across all the query types. The query types means that the pattern of the query graph we use for multiple reasoning. Like for 1P, it means that just like a simple single hop reasoning, and 2P is like you do a chain, two projection reasoning, and 3P is even longer one. And like the example we used here, this kind of query is called intersection plus a projection query. So it corresponds to the query type IP here. And these are the results. And as a byproduct of our model, it can predict the number of answers out of the box without supervision, because we can always take the cardinality of the fuzzy set to predict the size of the fuzzy sets. And we evaluate this just the following standard benchmarks, try to measure the sphere mass rho between the our model's prediction and the choose number of answers. And it can also provide interpretation for its prediction, because we can simply just take the elements with the top probabilities in the fuzzy set, and we can visualize the predictions. We can say, okay, A is corresponds to these entities, B is corresponds to these entities, and C corresponds to these entities. So this is all about my presentation today, and yeah, personally, I believe like PaaS and the JS might have a bright future for graph reasoning, especially when the last few years are just saturated by neural embedding methods, and people feel somehow frustrating with that. And it may also provide inspiration for other related fields. I don't know if any of you work on this kind of field, but I guess it might be related to algorithmic reasoning, like trying to use graph neural networks to solve shortest path problems or solving spanning tree problems. And also it might be related to combinatorial optimizations on graphs, using the idea of combining dynamic programming and graph neural networks. And it may also be helpful for downstream tasks like natural language understanding. You can equip a pre-trained language model with this kind of node graph reasoning model and with the external node graph so that you can do reasoning more efficiently and also more powerful. And all the code of this talk, the MBFN is already released on GitHub and the GNQ is still under construction, but I guess it might be released just in 1 or 2 weeks. So any question?